Now let us discuss the formulas used to calculate lateral earth pressure. To determine the lateral earth pressure exerted by soil, we must first calculate the lateral earth pressure coefficient, commonly denoted as K. Let's begin with the at-rest earth pressure coefficient, which is represented as K0. The most widely used formula for K0 is the Jackie 1944 equation, which is 1 minus sine of phi prime, where phi prime is effective internal friction angle of the soil. This formula is valid for normally consolidated or NC soils. However, for overconsolidation effect or for overconsolidated soils, the overconsolidation effect must be considered. To account for this, two commonly used modifications were proposed by Main and Kalhavi in 1982, which adjust the normally consolidated value of K0 by multiplying it to OCR to the power of sine of phi prime, or more simply, by multiplying it to a square root of OCR. And OCR is the overconsolidation ratio. Another useful formula, particularly for cohesive soils, was proposed by Massarge in 1979. This approach involves the plasticity index, Pi, and as you know, Pi is LL minus PL. LL is the liquid limit of the soil and PL is the plastic limit. Since Pi is only defined for cohesive soils, Massarge's method is applicable to these soils types. As shown in the diagram on this slide, the at-rest lateral pressure distribution is triangular, with the maximum stress occurring at the base of the wall. The magnitude of this stress is given by K0 times gamma times H, where gamma is the unit weight of the soil and H is the height of the wall. The resultant force from this triangular distribution acts at 1/3 of the wall height from the base. When water is present behind the wall, either fully or partially submerged, its effect must be incorporated. Conceptually, we can consider water as a soil with no shear strength, implying an internal friction angle of 0, or phi equal to 0. Therefore, K0 for water would be 1 minus sine of 0 degrees, which would be equal to 1. This aligns with the fundamental concept from fluid mechanics. At any depth, the lateral and vertical pressures in water are equal. In contrast to soil, this causes hydrostatic pressure to act fully on the retaining wall. This illustrates the critical importance of drainage and dewatering. Neglecting drainage often results in significant water buildup, exerting large lateral forces on the wall, sometimes leading to structural failure. Below the groundwater table, the effective unit weight of the soil, or gamma prime, must be used. Gamma prime is equal to gamma sat minus gamma W, where gamma sat is the saturated unit weight of the soil and gamma W is the unit weight of water. The total lateral pressure at any depth below the groundwater table becomes a combination of K0 gamma prime times H2. Let's say we are at the bottom of the wall. This is effective stress from submerged soil. Then gamma W times H2, which is the hydrostatic pressure from water, and any pressure from unsaturated soil above the water table. Here it would be K0 times gamma times H1. These are shown here, and as you can see in the green line on the graph, the slope of the pressure distribution increases below the groundwater level. This slope is steeper than this one. And this is because of the effect of hydrostatic pressure from the water. Now let us consider the lateral earth pressure coefficients for the active and passive cases. We begin with the Rankine's theory, developed in 1857, which is one of the most commonly used methods for calculating lateral earth pressures. Rankine's theory is based on the assumption of plastic equilibrium in a soil mass and assumes no friction between the wall and the soil, which is a key simplification. Under Rankine's assumption, the angles of the failure surfaces are as follows. For the active case, the failure surface makes an angle of 45 plus phi prime divided by 2 with the horizontal. For the passive case, the angle is 45 minus phi prime divided by 2 because a larger soil wedge is mobilized during passive resistance. The formula for the active lateral stress at depth Z is sigma A, which is equal to gamma Z Ka minus 2 times of C square root of Ka, where C is the cohesion of the soil. And Ka is the active earth pressure coefficient, which can be calculated using these formulas. These formulas are the same considering the trigonometric relations. For the passive lateral stress at a depth Z, the formula becomes sigma P equals to gamma Z Kp plus 2 times of C square root of Kp. Note that the sign before cohesion term is positive here, unlike the active case. The coefficient of Kp, or the passive earth pressure coefficient, is given by these two formulas here. And as you can see, Kp is the reciprocal of Ka, or Kp is equal to 1 divided by Ka. Now let's briefly compare these with the at-rest earth pressure coefficient, or K0, which is 1 minus sine of phi prime. If you compare K0 with Ka, we can easily understand that K0 is larger than Ka, because Ka is basically K0 divided by a value which is larger than 1. And also Kp is larger than K0 and Ka, because Kp is 1 plus sine of phi prime, which is larger than 1, divided by 1 minus sine of phi prime, which is smaller than 1, and it would be significantly larger than K0 and Ka. These relationships are fundamental to understanding wall-soil interaction and designing safe retaining systems. Let us now compare the values of Kp, K0, and Ka using the schematic figure shown here. Imagine a man interacting with the retaining wall and think about the amount of force he needs to apply under different conditions. For active earth pressure, if the wall moves slightly away from the soil, such as during excavation, the soil relieves some of its stress. In this scenario, the man needs to apply only a small amount of force to hold the wall back, just enough to balance the reduced pressure from the soil. This reflects the smallest lateral pressure condition and corresponds to the lowest coefficient, which is Ka. If the wall is held in place without any movement, the soil is in a natural state of stress. The man now needs to apply a moderate amount of force to maintain equilibrium. This situation reflects the intermediate value of lateral earth pressure, or K0. Now consider the man trying to push the wall into the soil. As the soil resists this motion, a significant amount of force is required. This case corresponds to mobilizing passive resistance, which is the maximum lateral stress condition and requires the highest pressure, which is Kp, and therefore Kp is the largest of the three coefficients. This intuitive analogy helps reinforce the physical meaning behind the numerical values of the earth pressure coefficients. Ka is associated with minimum resistance, or wall moving away, K0 reflects the natural or at-rest condition, no movement, and Kp involves maximum resistance, wall pushing into the soil. So the formulas and numerical values we use are fully consistent with our physical experience and common sense, which is always a good sanity check in geotechnical engineering.